welcome to the Climate Change webinar series organized by Pire Create Project. I'm Natalia Ruiz, Project Manager, and I want to thank you for joining today's webinars, Visualizing Change, Transforming Data into Actionable Information. During this webinar, we're going to learn how can we use visualizing tools to communicate science to different audiences, focusing on policymakers. We're lucky to have a large number of experts participating in the webinar. So I encourage you to ask all your questions through the chat, and at the end of the session, we will be able to answer them. Let me introduce you to the speakers we have for today, starting with Mathias Vuille, Pire Create Project Director and Professor at the Department of Atmospheric and Environmental Science at SUNY-Albany. Ernesto Tejedor, Postdoctoral Research Associate, Department of Atmospheric and Environmental Science at SUNY-Albany. Kyle McCUEY, Research Support Specialist at SUNY Center for International Development. Ryan Taylor, Associate Professor of Environmental Study at Purchase College. And Adam Toubey, Program Manager at Albany Visualization and Informatics Labs at UAlbany. Having made this introduction, Mathias Vuille is going to make a brief introduction about the Pire Create project. Thank you.
Thank you, Natalia. I assume that some of you may already have participated in the first or the second webinar, so this may be a little bit of a repetition. But for those of you who are joining us for the first time, I would like to just give a brief introduction into the Pire Create project, what it is and what we like to do in this project. So Pire, it's an acronym. It stands for Partnership in International Research and Education. It's a program that is sponsored by the National Science Foundation to enhance interdisciplinary research in an international setting. So we're a group of scientists from different schools in the US that collaborate with the partner institutions in South America, in Brazil, and also in Argentina. And the main focus of our project is to reconstruct how climate has varied in the past and why it varied in the past in North and South America over roughly the last 1,000 years. And the reason we're doing this is because we want to understand how unusual the climate of today really is. And we can't understand that by just using data from weather stations, temperature and precipitation measurements, because these records are so short. They only go back about 100, 150 years. And this entire time period coincides with the Industrial Revolution, with our emissions of greenhouse gases. So none of these records really record just the natural variability. So we need to use these natural archives, tree rings, cave sediments, and others to put the current record into a much longer term perspective. That's sort of the research goal of this project, but we also have an educational and an outreach pillar. And in the education component, we try to engage students, undergraduate students, graduate students in our work. We tour different SUNY campuses to get undergraduate students engaged in hands-on activities. In a fun weekend, we went to Professor Ryan Taylor's school last year, Purchase College. We were planning to go to SUNY Oswego this year. Hopefully we can do it next year instead. We organized summer schools abroad. We went to Brazil with our students last year, did work in the rainforest. This year we were hoping to go to Brazil again because of the pandemic. We will now are planning to do this next year. And the third pillar is outreach, and that's sort of what this webinar today is all about, to try to not just do research, but translate our results into visualizations, into a language that also policy and decision makers can understand. So with having said that, I'm going to hand over, I think, to Ryan Taylor, who will give a little bit of more of an, or actually to Adam first, I'm not sure.
I got it, Mathias, thank you.
Thank you.
So just as a refresher for everybody, the last couple of webinars that we've done, during our first webinar, we learned a lot, and Mathias did some fabulous presentations for everybody, all about the different congruent data sets that lead climate scientists to be able to monitor the ways in which climate changes. During the second webinar, we talked a lot about went into some of the details about how scientists go about collecting those data. And so one of those particular data sets was dendrochronology or tree ring data. But the first talk was mainly focused on what data sets do we use, then how do we get the data? And over both weeks, you saw a lot of examples presented by our scientists of the different data sets. And each one of those examples have been visualized in different ways based on the limitations of the data, whether the limitations be about the amount of time that they cover, or about the nature in which the data was collected. And some of those data sets we've talked about so far have been things like instrumented readings, thermometer measurements, phenology observations, or journals collected that talk about blooming and emergence of various parts of nature. Or you know, what we could refer to as the stress or the responsive nature to the climate. We've talked about cores taken from coral reefs or lake bed sediments, and ice flows and cores of ice structures, and then also about speleothems and then of course the tree rings, which is the main part here. And so one of the main points, if you tuned into last week's webinar, was there was a lot of emphasis about scientists sharing data with one another. How do they share information with one another? And so one of the goals of Pire Create has been to help create a data visualization tool that will allow the scientists to take the data that they've been collecting and share it, not just with other scientists, which is sort of the norm for our field, but to also share it with the general public and with policymakers, and then hopefully doing so in such a way that laypersons and policymakers can understand what it is the scientists see and how they work. As a general rule, scientists don't do a lot of sharing their results with the general public. We tend not to be as comfortable with that step, and so when you go through the process of sharing a graph or creating a tool for accessing data for other scientists, you think about it differently than the way you might think about designing a tool for sharing with the general public. And so you have to think about the end use of the data, and you have to think about the potential interests those folks have. So what we hope to do today is to show you 3 different tools that that have been developed by these teams to talk to you about the climate data that we're going through and that we're going to be going over with you today. And so I just want you to keep in mind that these are tools that have been specifically designed for the purpose of trying to make these relatively complex concepts related to climate change accessible to everyone and hopefully actionable by decision makers. So Adam, do you want to talk about the 3 tools at this point?
Yeah, absolutely. That'd be great. So I work with Vuille. It is the Albany Visualization and Informatics Lab. We specialize in taking data and visualizing that data for people. So the 3 visualizations that we're going to be looking at today are the tree ring viewer, which is a depiction of NOAA or the National Oceanic and Atmospheric Administration's tree ring and speleothem archives. Next, we're going to look at the forest stress tool that's going to visualize over centuries worth of international tree ring data to analyze historical tree growth. And then finally, we're going to look at a visualization of paleohydrodynamics data assimilation product known as FIDA. This tool maps 2,000 years of reconstructed hydroclimate and associated climate dynamic variables onto a global interface. So without any more introduction than that, I really want to jump right into these tools. There will be a question and answer section at the end. So if you have any questions, feel free to put those in chat and we'll jump on them. Okay, so this is our tree ring viewer. Right now, we use a map of the entire world because this data set is all around the world. It's each one of these points is a different site that has had core samples collected from trees. So each of these dots can have between 20 and thousands of samples per site, and there are over 230 unique species in the data set. Because there are so many species that we're dealing with, we decided to add a filter so you can filter by the species, and you can pick something specific like blue oak, and then move into where blue oak samples have been taken. Hovering over each of the points, we're given a little bit of information from the metadata, such as the name, who took the sample, what kind of tree it was, how old the tree is. And from there, we can click into each one of these and learn a little bit more about them. So as we're going along today, I'm going to be giving us the framework, and then our other guests are going to be sort of building the story that the data tells us. So inside one of these, we have the chronology of the tree. And this chronology is, of course, lends itself very well to being on a timeline. With the, what you're looking at here, this disk, is a core sample that's been taken from a tree. And I think it's important to note that the trees are not cut down to take this core sample. It's just a small line that's been taken from the center of the tree, and that line has been rotated along the center axis to give us a visualization of that core sample, with darker indicating more growth. And then inside each of those points that we click on, you can see that we have many, many different samples of trees. And you can see that some are older, some are newer, as shown on the timeline at the bottom of each of the sample. The start year of each is listed up at the top.
Adam, if I can jump in here for a second while you're kind of looking at that.
Yeah, please.
A couple of things here. Keep in mind, when the scientists, the dendrochronologists are collecting those samples, the cores, it's only about the size of a pencil. They're drilling into the pith of the tree and taking a sample about the size of a pencil. And really what they're, in terms of diameter. And so this is just a drawing of what would that pencil look like if you were to like cut a disc through the tree. And then the other thing, could you scroll down a little bit here on some of these samples? If you notice, yeah, you can see that each different tree ring, each disc that you have represented here, they are showing different periods of Earth's time. And so the far right, you've got to 2000, and that each different disc only has a certain amount of the record in it. You just scroll down a little bit more for one more slide. And then here you can see, here you have 3 discs that are all represented the same size. Meaning the diameter of these 3 discs are all actually the same diameter, or the trees have the same radius in real life, but they grow at different rates. And so the tree ring on the far left there, it grew and put on much more wood over a shorter period of time than the tree ring on the far right. It took a longer period of time to put on the same amount of wood. And then you can see in the fluctuation there in the tree ring in the middle, at its early years of its life, it was putting down a whole lot of wood when it was young. And then later in life was putting down a little bit less wood. And so you can see the fluctuation on growth being expressed on the y-axis of those blue lines, amount of growth per year and that's correlating then with the colors that are being represented in the rings of the disk.
Great, thank you, Ryan. Okay, so Mathias, did you want to give us a little bit of information, a little bit of background on the Denison Peak site?
Sure, I can do that. So when scientists take cores like this, they basically do that because they are interested in extending the climate record back in time. And in case you missed some of our early webinars, so basically the idea here is that when the climate is favorable for the tree, it will grow a large ring. However, when the climate is unfavorable and is environmentally stressed, it will grow a very narrow ring. So this blue line that you see here is the average of all these records that are shown below. So whenever you have a peak here, it means that in that particular year, the tree added a large ring, while when you have very low values, the tree grew just a little. So the question now is what is the climate signal that these trees in this particular location are recording? And at this particular site, these blue oaks in California, these records were initially developed by David Staley and his team. Professor Staley is a dendrochronologist at the University of Arkansas, one of the leading specialists in his field. And in their early work, they were able to show that these blue oak trees respond in a very sensitive way to hydroclimate, because they're moisture stressed. So in this early work, it became clear quite quickly that these trees are good indicators of wet and in particularly dry locations, rainfall in California, and also stream flow in rivers in California. And Adam, maybe you can go to the next slide now, PowerPoint slide. Following up on this work, looking just at some of the trees that grow at higher elevations in the Sierra Nevada, Sumaya Belbecheri and a team of scientists from the University of Arizona, they were able to show that these trees are actually also very sensitive to the amount of snow that is falling in the Sierra Nevada, which makes sense because they are moisture limited, and if you go up high enough, the precipitation will not fall as rain, at least in the winter, but it will fall as snow. So what you're seeing here in this figure, there are three lines from 1930 to about 2015. The blue and the red line, they're almost identical. They basically plot on top of one another. And what they show is the amount of snow that is stored in the Sierra Nevada at the end of the winter on April 1st. And the way we measure this is what's called snow water equivalent, or SWE. That is basically the amount of water that is stored in the snowpack. The blue line, it's just the average from over 100 station measurements across the Sierra Nevada. Now, scientists sometimes like to make things a little bit more complicated. So rather than just taking the average, we can also try to take from all of these records the signal that they have in common. And the way scientists do that, they use a statistical technique called principal component analysis. So the red line shows the so-called first principal component, the signal that all these records have in common. But it's basically also an average. You can see that the red and the blue line, they basically show the same thing. So these are actual measurements of the amount of snow stored in the Sierra Nevada each year on April 1st. Now, the scientists looking at this, they realized that with tree rings, we can reconstruct this amount of snow. So they developed a simple linear model, so-called regression model, and they tried to reconstruct the amount of snow using tree rings. And that's the black line that you see here that only goes up to 1980. And you can see that this black line really mimics what we see in the actual measurements. So we can reconstruct quite well with tree rings the amount of snow that is stored in the Sierra Nevada. And now you can go to the next slide, please. The reason why this is important is because we only have measurements of snowfall in the Sierra Nevada that goes back to 1930. But with the trees, we can now reconstruct this amount of snow all the way back to the year 1500. And that's what's shown in this black time series here. The red are the observations that only go back to 1930. And if you look at the very end of this time series now, the last year, 2015, where you have a very, very low, very negative value where that cursor is, you can see that this year was the lowest snowpack on record. If you follow that dashed line back all the way to the year 1500, you can see there's a couple of years there around 1580 where the gray shading, that includes the uncertainty, surpasses that line. So there's a small, slim chance that then we had equally dry years. But most likely the year 2015 was the year with the lowest snowpack in the Sierra Nevada of the last 500 years. And the snowpack, of course, is really important for water resources in California during the spring and the early summer. And without the tree rings, we wouldn't know this, right? It's only thanks to the tree rings that we can actually put what is happening now in this really long-term perspective. So it's one example of how we can use tree rings to put what is happening now in a long-term context. And I think Ernesto will now give us a second quick example where trees are used for a different purpose to reconstruct temperature.
Thanks, Mathias. Hi, everybody. Yes, Adam, if we can go to the tree ring viewer, to some of the northern Scandinavia, or well.
Yep.
Just...
All right. So I've gone up. We've looked at all species and the site.
All the species. Just to mention that the species and the trees will be limited, or their growth will be higher or lower according to the environmental conditions. And some examples, like the one that Mathias showed, those trees there, according to their location, they were more limited by the hydroclimate, so by the amount of precipitation in this case that had there. But in other locations, such as in the high latitudes, these trees will be more limited by temperature because they don't have problems in terms of soil moisture. They have good precipitation amounts during the whole year. So they will grow more or they will grow less according to the temperatures of that year. If the temperatures are good enough, are positive, they will grow more. If the temperatures are colder, are negative than usual, they will grow less. So we have very, very ancient trees in these locations. And just to show an example that we can build temperature reconstructions in these high latitude locations. And I don't know, Adam, can you go to the slide of the other slide? Yeah, that one. So you can see there 36 triangles. Those are sites that you have in the tree ring viewer. So with these sites, those trees over there, they are sensitive to temperature. And with each of these sites, we build 36 reconstructions of temperature that extends over the last millennium, so the last 1,000 years of summer temperatures. And this is crucial because now we can place the current warming that we are facing into a long-term context, and we can highlight the increase in these summer temperatures in a very, very long perspective, and then attribute that to other causes, such as we saw in the last webinar. And if we go now, we can, I don't know if Kyle or Ryan, do you have something to add on this, or otherwise we move to the forest stress?
I just want to add one quick thing about the timeline that we're working with here is that, you know, those species, the blue, what were they, blue spruce, was that right? No, not blue spruce, blue pine.
Blue oak.
Blue oak, thank you, blue oak in California, right? They were able to allow us to recreate back to 1500, right? Like we can go back to when the Spanish were starting to settle California, starting to settle the Nevada, settle that area. And we could take that and look at what we know as sort of a foundation for creating our modern civilization in that area, right? And that this data set now lets us push it back yet another almost 500 years further than that. So for people who talk like instrumented data is the only data, the data that is only collected during the last, since 1930 or 1860, here we can say, no, this is real good data showing us how the climate has performed over much longer periods of time. And even though we have been interacting with these data sets, looking up specific species because we're scientists, the tool would allow a policymaker or allow a layperson to access based on where they live, to go and say, I don't know about the species, but I know where I live and I want to see what's going on here, and could see tree rings performing differently over time.
Yeah, thanks.
Great. So that, I think it's I think we can move from the tree ring viewer, which I have right now, the tree ring viewer looking at near Chiang Mai in Thailand. And if we move over to our forest stress tool, you note that the points are the same points. So, well, the tree ring viewer is almost a catalog or a sample viewer. We're now taking those samples into our forest stress viewer, and we're going to add analytics to them. Now, I'm excited to show you this tool, but it's also important to remember that this is a tool that's in development. This is cutting edge climate change analytics, and you're getting to see a tool while it's still being developed. So there'll be some components that we'll have to show you via slideshow that just aren't done yet. And it's fascinating to see that. So Ernesto, do you want to run us through some of what the Synchrony means and how we can use that?
Yes, thank you, Alan. So we know that climate change impacts extend well beyond an increase in temperature or changes in precipitation regimes. So climate change is also impacting the forest ecosystems around the world. And we know that our forests offer many valuable services. Forests are very important globally. And for instance, trees are carbon pools, carbon sinks, capturing the CO2 that, you know, it's the main greenhouse gas warming up our planet. So we have this incredible data set provided by all the scientists that share their data that collected for years. So we can now take that data set, that global data set of the different forests around the world, and study or evaluate how the climate change is impacting or not this forest ecosystem. To do that, we use a concept that is known as Synchrony, and this concept relies on the assumption that the world around us is spatially autocorrelated. So this means that we call this asynchrony, and this means that a forest with high synchrony will be more environmentally stressed, and a forest with low synchrony, its growth will be less environmentally stressed. And here in the map, you see multiple dots with different colors. You have the legend there, and this legend is indicating with red colors that they will have a high synchrony, the forest, and with the blue colors, it will indicate that it has a low synchrony. So in other words, the red colors are indicating that those trees on that particular forest are more environmentally stressed within these last 100 years. So that means that the growth of that particular forest is very limited to the climatic conditions. And we can put that, if you want, as in terms of risks. If we know that climate is warming up, so these trees are perhaps more in risk of for different reasons. And so we have here the observations that are the places that many scientists have collected around the years. And we can then see how this synchrony have changed during the instrumental period, during the years that we have weather data. And please, Alan, you can click the change. So here we can see that some of these sites have already changed during the last 100 years. And we find with this study that the change on synchrony and the explanation of how these trees are environmentally stressed is due to the annual precipitation and due to the annual temperature. And so what we are seeing here, it's not representative of all it's representative of mainly all the forests around the world, but we don't have samples in all the forests around the world. There are large gaps, like in South America or in Africa, that either scientists haven't been able to collect samples there, or they are just not stored yet in this data set. So what we did here is we create a model that we apply to the whole forest cover around the globe. So Adam, if you can go to the model, to the current climate. Well, yeah, we have this to explain, try to explain better so you can understand the synchrony. We have here 3 pictures. One that is in the top left, it's Priestley pine from the Nevada mountains. And this is an example of environmentally stressed, high environmentally stressed trees. And we call these very high synchrony locations. These trees, as you see, they live in a very harsh condition, and so they will grow very synchronized between each other only when the conditions are good. We have in the middle, the moderate synchrony. These trees, they grow very well, but they are not very, very synchronized, but they are not too environmentally stressed. And then on the bottom panel, we have an example of what it could be very low synchrony, like for example, the rainforest in the Amazon. Those trees there, they have enough precipitation, they have good temperature to grow, so their growth is not synchronized. The environmental conditions are not their main limiting factor, so we call this low environmentally stress or low synchrony. And if you can go, Adam, to the model, I don't know if we can show the current synchrony. So what we did here is we learned that this synchrony can be explained by the climatic factors like temperature and precipitation. We know the forest cover around the world, so we apply our model to all the forest cover and even to those locations where we didn't have samples to analyze. So, for example, we apply this to the South American forest that we didn't have samples, and we learned that the synchrony of those forests in the Amazon, for example, is very low right now. And we say, okay, we know how is how these trees around the world are environmentally stressed or not. Now let's do the exercise. Since we know and we have future climate projections, let's see how this global forest extent will change if we now apply our model, but including the future climate instead of the current climate. And what's more interesting here is that we can then see which of these forests are going to undergo changes in the environmental conditions and which trees or which forest ecosystem will be more environmentally stressed. And Alan, if we can go to the, so this is now, this will be the last model I will be showing in the forest stress viewer. And in this figure, what you can see is that some forests will increase their synchrony, so they will be more environmentally stressed, and some will be less environmentally stressed. So an example of these trees that will be more environmentally stressed, it's on the Amazon basin. We know because of the future climate projections that this particular region will have less precipitation amounts and an increase in temperature. So those trees there, they will have to find more for the resources, and they will have more problems for growing as much as they want. So they will be more environmentally stressed. And what that means is that they will have less capacity to act as carbon pools. So less capacity to sink the CO2 of the atmosphere. And the opposite might be true also for the temperate forests, that they will benefit from an increase in temperature, and they will be less environmentally stressed, and they will face then other problems like competence or fires or insect outbreaks. I don't know, Kyle, Ryan, if you want to mention something here.
I'll add that, you know, one of the wonderful things about this expansion, this tool, is that I want to emphasize here is that we are able to model all these places that we didn't have direct observations for. And so if a policymaker was using just the tree ring viewer previously, or a layperson, they may just see those data points and say, oh, there aren't any data points where I am. And so I can't know anything about how my climate is changing from this data. But when we look at the tree ring viewer, you know, when we look at South America and Africa, those are two huge continents with a lot of holes in the data. And that when we look then at the model allows us to take this data that was collected and make it actionable in places where we can't get boots on the ground to do the field collection, where we can't go in and we have not yet been able to take observations and put them into the model. And I think that's a very empowering part of this tool, is to say that we can know places that we don't have direct observations from. The one thing that folks do need to, I think, be aware is that the places where there are no color here, where it's blank in the terrestrial areas, those are just places where trees don't grow. And so it's not that those are places for which we don't have data. It's places for which we can't apply the model because the climate conditions are not sufficient for trees to grow in those places. We don't have a forest cover in those places that are blank. So our model doesn't extend to how trees would be stressed in those places because we don't have an existing forest to talk about how the stress would be changed.
Yeah, thanks.
Great. So we've looked at, the tree ring samples in point basis, and then we look at now these observations and these models in a regional perspective. And now I think we should transition to looking at things on a global scale. So this is the FIDA data. This is a conglomeration of tree ring, cave sediments, pollen data, ice cores, coral records, lake sediments. All of that has been put together to give us a more comprehensive and more holistic model of temperatures around the globe. So of course we use the traditional blue is cool, red is warm, and we have on the left-hand side the global mean temperature on this timeline for the chronological data. Within the timeline, you can look at each individual year and see what the global mean temperature was for that year. And then additionally, we can click on a point and see, or click on a year and see how that year differs around the world. We can change to our global anomalies now, and we can start to look at, based on year, what kind of global anomalies are happening using a base range of 850-80 and 1850-80. So the year 1601, would you guys like to give a little bit of an explanation of what's going on in this?
Sure, maybe I can chime in and just give a little bit more background information on the tool that we're actually looking at here.
Sure.
So this is, you can see we have a globe here in front of us and we have information everywhere. It's spatially complete. There are no gaps. So underlying this data set is an actual climate model. And climate models are great in that sense that they give us information that is spatially complete. You can get information on the climate in any given location at any time over the period that you run the model. But models also have a lot of problems, uncertainties, and as we just talked about before, to really understand how the climate changed in that particular location, it's better to use these natural archives, such as tree rings. But these natural archives have a lot of gaps in space, as Ryan and Ernesto pointed out. We don't have trees over the ocean. We don't have trees over deserts. So a lot of places we lack information. So this product that you're looking at here that was developed by Nathan Steiger and Jason Smirden at Columbia University a couple of years ago, it actually merges these two data sets to take advantage of the strength of each data set. So it is a climate model, but at every time step, the climate model is being informed from the proxy data what actually happened. So you can think of a climate model that is being nudged or corrected at every time step. So we're basically trying to keep the climate model honest and improve it. So it's sort of merging the best of two worlds, if you will. But now, yeah, we can maybe look at a couple of examples. So maybe Ernesto can talk a little bit about what happens during a volcanic eruption.
Yeah, so what's interesting with this type of data set is we can explore the temperature variability or the hydroclimate, because it also includes the hydroclimate information that will be released soon also in the viewer. So we can go back in times that we know that there were huge volcanic events, for example, because we know with the instrumental data that the volcanic events affect and impact climate. For example, when in 1991 there was this huge volcanic eruption of the Mount Pinatubo. Yeah, so these volcanic eruptions release gases and sulfur dioxide into the troposphere that eventually reach the stratosphere. And so in the stratosphere, sulfur dioxide it's very effective. It's much more effective than ash particles at cooling the climate, because now we have less incoming solar radiation to the Earth, and so the effect is one of cooling on the Earth. And so we can then evaluate the impacts of these large volcanic eruptions that have happened during the last millennium or the last 2,000 years, and we can try to understand the impacts that these events have on the Earth climate system. And you know why? Because these large volcanic eruptions are going to happen in the future. And we need to be prepared for the risks and the induced climate changes that these large volcanic eruptions will have on the impact on top of the anthropogenic activities. So we can, for example, you can go to 1998 to see the current warming period. So you see that the anomalies, the Earth is red. That means that the anomalies with respect to our base period are positive. So this is, this is 1998, but we can make it as an example of today's climate. So we see that in almost all the Earth, there is warming. This is almost, the warming is synchronized almost in every part of the world. So the volcanic eruptions have that power to synchronize, instead of warming, cooling. So now if we go to 1601, this is 1 year after one of the largest volcanic eruptions of the last 1,000 years took place. And the eruption was in Peru. It was the Huayna Putina volcano. That volcano happened in January or in February of the 1600, and the next year you can see very, very negative anomalies all around the world, because it released so much gases and sulfur dioxide into the troposphere and eventually the stratosphere, that it's like you have another layer into the stratosphere that prevents the solar radiation to, or it's reflecting the solar radiation. So we have more cooling around the Earth. I don't know, Mathias, if you want to add something on this.
Maybe we could just show that you can actually click on the map and you can get the temperature record from a specific location, and that this is not necessarily representative of a global average. So when we talk about global climate change, we have to be aware that we cannot take temperature measurements from one specific location and think that this is representative of the planet. We have to look at it as a whole. So this tool also shows that. And again, I just want to emphasize that by merging the model with the actual proxy data, we have a data set now that spans 2,000 years, long before we made any measurements of temperature on this planet. And it's really a unique way to try to reconstruct, in this case, temperature, but soon we'll also have informations on wet and dry conditions up here, hopefully.
And Mathias, so interpreting this green line down below, someone could see, like for their location where they live, they could see how they may, if they're in a red area, that their green trace might diverge from the global average. And they could see how, boy, right now in these years or this time, I'm a lot warmer than the global average because my green line has departed above the white line. And they could then look back in time to see, is that departure normal or is that departure recent? The rest of the time, does that green line lie on top of the white line? But only in these last few decades has it shown to diverge. That someone could see that on a place-by-place basis. They could say, this matters here. This is what we are experiencing here with this data, right?
That's absolutely correct. I think one thing we can really highlight with this data set is that, as Ernesto pointed out, showing the year 1998, that we are now living in a world that is showing a very unusual climate, a very warm climate everywhere, virtually everywhere on this planet. We've had periods when it was very warm in the past too, but it was always limited to smaller specific regions. And we never had a situation where the entire planet was warming up this much everywhere at once. The other thing I want to add, just as a slight word of caution here, of course, what is not shown here is there are uncertainties associated with these estimates. And I'm sure the authors of this, Nathan Steiger and Jason Smearden, would be the first to acknowledge this. Some regions on this map, we have better information. In other regions, the uncertainties are larger, in particular in those regions where we don't have a lot of proxy information. So we do have to take this with a grain of salt and some caution that we don't overinterpret the individual records at any given site.
So right now, I'm just going to go ahead and set our base anomaly range to 850 and 1850. And, starting at the year 1601, I think it's cool to just show off some of what this tool can show us as we begin to look through and jump through these years. And you begin to see a very, very gradual pattern. And I think we should probably start it a little bit higher too.
And I know folks like to think like global climate change, like it's one thing, right? That one of the things this highlights is that location matters, right? And that it's not, you can't say one data point from one place tells you the whole Earth, but that is especially true in the atmosphere, which is a fluid. And so you are talking about the movement of air masses, movement of fluids that have different densities, that have different temperatures, that are interacting with one another. So it's going to look swirly because we are modeling the atmosphere. We're not modeling necessarily a solid.
Great. Okay, so I know whenever I am in a webinar and I'm getting to see these cool tools, one of the things that I really want to know is, hey, can I play with these tools? Are these something that I can play with right now? And the answer to that is yes, absolutely. So I'm going to be putting the website up so you guys can go online and you guys can check out these tools and play with them yourself, kind of mess around with them. You can give us any feedback you want. Did anybody else have anything they wanted to add before I move away from this? There's the website right up there for you guys.
Okay, thank you, Adam. Right now we have a question. I think maybe Ernesto or Mathias can answer it. How does deforestation impact Synchrony?
Thank you, Chloe. That's a very good question. It's a hard one because it depends on where that deforestation is taking place, but it will have a huge impact because deforestation is helping or is changing the climate, at least locally. So that will impact also the trees that are nearby. On the other hand, when we in this study we don't study the trees that are being logged. So or let me put it another way, we don't study the tree harvest. We only study the natural forest, because when you have all the trees growing at the same distance and with the same climate, they will grow very much the same. They will be very synchronized. So that's not the case with this study.
So thank you, Mathias, Ernesto, Kyle, Ryan, Adam. Great talk. We will upload these 3 webinar series into our YouTube channel and website soon, so you can stay tuned. Also, you can follow us or in our Instagram channel and visit our website to be aware of all the new scientific contents, new publication, expeditions, or educational programs that we offer to the students. So I think that's all for today. Thank you so much for joining us and have a good week. Bye.